First, mutual exclusion. The mutual exclusion condition must hold. That is, at least one resource must be non-shareable. Shareable resources, in contrast, do not require mutually exclusive assigns, and thus cannot be involved in a deadlock. Read-only files are a good example to shareable resource. If several processes attempt to open a read-only file at the same time, they can be granted simultaneously assigns to the file. A process never needs to wait for a shareable resource. In general, however, we cannot prevent deadlocks by denying the mutual exclusion condition because some resources are intrinsically non-shareable. For example, a mutex logs cannot be simultaneously shared by several processes. Section 2. Hold and wait. To ensure that the hold and wait condition never occurs in the system, we must guarantee that whenever a process requires a resource, it doesn't hold any other resource. One protocol that we can use requires each process to request and be allocated all its resources before it begins execution. We can implement this provision by requiring that system calls requesting resources for process precede all other system calls. An alternative protocol allows a process to request resources only when it has none. A process may request some resources and use them. Before it can request any additional resources, it must release all the resources that it is currently allocated. Both these protocols have two main disadvantages. First, resource utilization may be low, since resources may be allocated but unused for a long period. Second, starvation is possible. A process that needs several popular resources may have to wait indefinitely, because at least one of the resources that it needs is always allocated to some other process. Third, no preemption. The third necessary condition for deadlocks is that there be no preemption of resources that have already been allocated. To ensure that this condition does not hold, we can use the following protocol. If a process is holding some resources and requires another resource that cannot be immediately allocated to it, that is, the process must wait, then all resources the process is currently holding are preempted. In other words, these resources are implicitly released. The preempted resources are added to the list of resources for which the process is waiting. The process will be restarted only when it can regain its old resources as well as the new ones that it is requesting. This protocol is applied to the resources whose state can be easily saved and restored later, such as CPU registers and memory space. It cannot be applied to printers and tape drives. Circular wait. The fourth and final condition for deadlocks is the circular wait condition. One way to ensure that this condition never holds is to impose a total ordering of all resource types and to require that each process requests resources in an increasing order of enumeration. To illustrate, we let R equals to R1, R2 till Rm be the set of resource types. We assign to each resource type a unique integer number, which allows us to compare two resources and to determine whether one precedes another in our ordering. Formally, we define a one-to-one function where n is the set of natural numbers. So we can now consider the following protocol to prevent deadlocks. Each process can request resources only in an increasing order of enumeration. That is, a process can initially request any number of instances of a resource type, say Ri. After that, the process can request instances of resource type Rj if and only if Frj larger than Fri. So here we have an resource order R1, R2, and R3.